Today we want to go a little bit further with this tangent line business. Remember that the tangent line is the best linear approximation of a function near a point. So let's call this linear function L of x. What we're doing is making a linear function that matches our function in its value and its first derivative. We're trying to match the function in its value and its first derivative. So I say too soon with the applause. So I just wanted to make this look more like a function with some function notation. So instead of saying y equals, I'm going to say L of x, L for linear function. Line, if line is short for linear function. I have both doors posted. So this is a linear function that has the same value of the function and the same first derivative. We can say it's going through the same place in the same direction. Same value and first derivative. It has the same value and first derivative. What we mean is that L at x naught is equal to f at x naught. It's going through the same point and going in the same direction. The line is going through the same point and in the same direction as f. L is going through the same point and in the same direction as f. That's how we could describe it in words. The line is going through the same point and in the same direction. What we mean in terms of calculus is that the value of the function is the same. L at x naught is equal to f at x naught. And in the same direction is the first derivative business. The slope of the tangent line is the slope of the line. So through the same point and in the same direction. Notice that the structure of L tells us these things already. So if I look at L of x as f at x naught, remember x naught is a constant. F at x naught is a constant. F prime at x naught is a constant. This is where the variable is. So if I evaluate L of x naught, here's where the x naught shows up that we're plugging in. So call those out in the same color. Then we start at f at x naught and we add f prime at x naught 0 times. So this x naught minus x naught part cancels out having to add any of this slope. So that piece is equal to 0. So when we plug in x naught, we get 0. We get f x naught. L at x naught is equal to f at x naught. That's all that's left right there. If we take the derivative, we find L prime as a function, L prime of x. F at x naught is constant, so the derivative of f at x naught is 0. If we take the derivative of x, we get 1, and all that's left is the constant. If we think of that, the only variable term in the linear function is f prime at x naught times x to the first power. So the derivative will be 1 times f at x, f prime at x naught, x to the 0 power. Remember, f prime at x naught is just the slope, the m. And this is saying that the first derivative of L is constant. This makes sense. L is supposed to be a line. A line should have a constant slope or a constant rate of change. If we think about a line, y equals mx plus b, then y prime is just m. 1 times m, x to the 0 power. So this linear function agrees with f in its value and its first derivative. That's what we want to have happen. Now we get to the part where I alluded to yesterday. If we want to upgrade from a linear approximation to a quadratic approximation, all we got to do is add another term with x squared in it. Suppose let's suppose we want a quadratic approximation. The first, I'm going to call it q of x because I don't really have a lot of creativity. So we want this quadratic approximation to agree with the function in value, in first derivative, and in second derivative. It's the same requirements that we want for our tangent line. Just add second derivative as well. So q of x, the first two terms are going to be the L of x. We saw that these two terms will make the quadratic, or make the linear function agree with the function in value and in first derivative. Same point, same direction. What we want to add now is the second derivative, but we have to divide by 2 for reasons. But this is a quadratic that will agree in 0th derivative, first derivative, and second derivative. This is what I want to have happen. I want q of x naught to be the same as f at x naught. I want q prime at x naught to be the same as f prime at x naught. Or q prime at x naught to be the same as f prime at x naught. The new requirement that I want is I want q double prime, the second derivative, to be the same as f double prime at x naught. So q of x has the same value, same first derivative, and same second derivative. This is all happening at x equals x naught. Let's make sure that this is true. If I plug x naught into q of x, I get f at x naught, but these other two terms have a factor of x minus x naught, which when we plug in x naught is 0. If x naught is 3 and I plug in 3, I get 3 minus 3, I get 0 as a factor in both of those terms. All that's left is f at x naught. Q prime of x. The derivative of this constant is 0. The derivative of x to the first power is 1 times that to the 0 power. So all that we're left with is f prime at x naught. The derivative over here, I have x to the second power. The derivative of x squared is 2x. So I have f double prime at x naught over 2. That was my coefficient. And then the derivative of x minus x naught squared is 2 times x minus x naught to the first. So notice that those 2's will cancel out. Looking ahead to the next step, those 2's will cancel out. If I plug x naught into q prime, I get f prime at x naught. And then this term goes to 0 because I got x naught minus x naught. I have 0 as a factor. This term drops out, and I'm left with f prime. If I take another derivative, so these 2's cancel. The derivative of x minus x naught to the first is 1 times x minus x naught to the 0. I'm left with f double prime at x naught. So, answering the question from yesterday, that's why we need to divide the coefficient by 2 to cancel out the 2 that was going to show up when we're taking the derivative because of the conditions that we want. Now we have a quadratic function that matches the function in value, first derivative, and second derivative. Any questions? How's everybody okay? This is future stuff. I'm saying this now, not so that you understand this now, but later on in chapter 10, when I'm like, I'll tailor polynomials to be like, oh shit, I remember that. This is just where we extend the tangent line to tangent higher degree polynomial. Any questions? My theory is that if you build your foundation correctly, later on, you can cover new material by saying, hey, remember old material? We're just going to do that. Here's how it works in the new environment. Instead of algebra being some new weird thing, we could just say, hey, remember arithmetic? And you'll be like, oh, yeah, that was no problem. I could be like, oh, great. We're going to do all those same things. Addition is still means addition. Multiplication still means multiplication. It's repeated addition. Multiplication distributes over addition. Remember exponents? Exponents is just repeated multiplication. That's why exponents distribute over multiplication. And we don't think of algebra as some new weird thing. It's connected to arithmetic. It's the same stuff. Any questions? Where do we go after quadratic? Cubic. What if I want a cubic approximation? If you're thinking, are we just going to add a third degree term to what we already have? That is absolutely all we're going to do. We're just going to go a little further. So I'm going to start off with my linear approximation. We need another term for the quadratic approximation where I had to involve the second derivative at that point, but we had to divide by 2 from that derivative stuff. Because we take 2 derivatives, we multiply by the 2, then we multiply by the 1, we need to cancel out that 2. Our next term is going to involve the third derivative. And if you're thinking we're going to have to divide by something, then yeah, we totally are. All we have to do is think about what we want to divide by. That's F triple prime. There's 3 little primes above the F. What are we going to have to divide by? Is it just the 3? Clearly, it's not just the 3, right? Otherwise, I wouldn't have said so dismissively, is it just the 3? Obviously not. What else we're going to be dividing by? Think about where it comes from and what the mechanics tell you. I'm going to take the first derivative. Derivative of x cubed is 3x squared. So I'm going to need to cancel out a 3, but it's going to be 3x squared. I'm going to have to take another derivative. So I'm not just have to cancel out the 3, I'm also have to cancel out a 2. So we're going to have to cancel out a 6. Normally we would write 6, but we want to remind ourselves of where it comes from. Now this polynomial is third degree, so we're going to have to take, we can take 3 derivatives before we end up with 0. So C prime of x is just going to be constant is 0. The derivative of your first degree term is just going to be your coefficient. 2 times 2 cancels out, and we have f double prime at x naught times x minus x naught to the first. 3 cancels out the 3, so I'm left with f double prime, or sorry, triple prime at x naught over 2 times x minus x naught squared. When we plug in x naught, all that's left is f prime at x naught, which is what we wanted. We take another derivative, c double prime. Derivative of a constant is 0. The derivative of this linear function, x to the first, is 1x to the 0. So we're just left with the second derivative. 2 cancels out the half, and we're left with f triple prime at x naught. But this is still times x minus x naught to the first. So that's why in the beginning we needed that 6 to cancel out the 3 and the 2 from our derivative process to make sure that when we land at the third derivative, all that's left when we plug in x naught is the third derivative at x naught. Remember in the previous ones, every time we plug in x naught, everything but the constant term has a factor of 0 in it. It's just left with the constant term. Any questions? Where might we go next?
I think that
No, it's never enough. This is calculus class. How far can we take this? To infinity. We just keep going. That's the calculus way. This is a better approximation than our quadratic, which was better than our linear, which is better than just the value of the function. So doing this more often means we get a better approximation. We'll just do it forever. We just make this go on forever. But then we have a polynomial with an infinite degree. So we can't call it a polynomial anymore. We just have to call it a power series. That's the other way that we have to study infinity in calculus. But you don't get to know that until calculus. If you don't take Calc 2 now, it'll be like Game of Thrones, where they set up some story element and then never address it again. I'm going to grab my family's ancestral sword. And then we'll never bring it up again. So, incidentally, if you become showrunners and you want to do some other project, just hand it off to somebody else. Don't say, oh, it's all over now. I mean, that's just how Dungeons and Dragons campaigns end anyway. So I guess it's kind of realistic. I guess it's true, the rumor that this is just a campaign that George R.R. Martin was running. And it just kind of fell apart because this campaign is grown-up players and not high school kids that can play every week reliably at lunchtime or something like that. You know what I mean? Only D&D players know what the hell I'm talking about, but that's okay. I don't mind if the references wander off to a place that no one understands what I'm talking about. I'm used to not being understood. I am, after all, a math teacher. So all we have to do is just keep this process going forever. There's a lot of liabilities that come up with going to infinity, because I mean, just the dot, 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 what the hell does that mean? But we see the structure of what we need. The next term would be these three. I'm not going to write the whole thing. So our fourth degree, I'll call it capital F at x. We'll start with, we need all the stuff from C of x. And we're just going to have a fourth degree term, which we're going to have our fourth derivative at x naught. At this point, there's too many primes to write 4 primes. So we just put a 4, but we don't want it to look like f to the 4th power. So we put it in parentheses. That's our notation for the fourth degree, sorry, fourth derivative of f as opposed to the fourth degree. What am I going to have to divide by? Considering that this one has an x minus x naught to the 4th power. We'll need to cancel out a 4, a 3, and a 2. That'll be 24. Our notation for that is 4 factorial, which is the unfortunate 4 with an exclamation point after the number. So we say 4. Actually, you don't read it that way. You should just say factorial instead of shouting 4. If I could, I would take a level of cleric just to get the thaumaturgy decantrip so I could make my shouting much more impressive. Be like, oh, 4. And like the lights would flicker. Door would slam shut. I'd light candles just so I could make them flicker. That would be exceptionally weird. You walk into math class and the teacher's like lighting candles. Everybody prepare yourselves. For today, we learn about Taylor polynomials. Dun, dun, dun. But then we get into it and you're like, oh, dude, it's not that impressive. It's pretty mechanical. The reason I like this is that this is another aspect of the calculus thinking. Here's how we approximate a thing. Here's how we improve the approximation. Calculus just asks a question. What if we do this approximation business? What if we just keep going? Just do it forever. Take this secant line. It improves by moving the point closer to the point we care about. Make it move infinitely close. That's a limit. We make a better polynomial approximation by adding more terms. How many terms? Infinite terms. Just keep going. This would require an infinitely differentiable function. Okay. So a tangent line is just a first degree Taylor polynomial. Approximating the function near a point. If you're interested in checking out Taylor polynomials, they're discussed in your book in chapter 10. Or you can go to the ultimate source, Wikipedia. Wikipedia is actually a great source for math things or science things in general, because no nerd is going to let incorrect information stand for very long. They're going to see something on Wikipedia and say, what? Pi is exactly 3? No. And then the person that wrote that will get banned from updating things on Wikipedia. It will not stand for long. No. I've been banned from Wikipedia. I'm just kidding. I have several fake Wikipedia accounts that I use to modify. I'm just kidding. I don't do that. Who's got time for that? Incidentally, you don't want to cite Wikipedia itself as a source, but Wikipedia has citations. So just scroll down and cite the paragraph that you're citing, right? I mean, it's not like this is just stuff that people are making up. It's stuff that they're repeating of someone else that made some stuff up. So that's how it works. But seriously, the math information is pretty good, if a little bit dense. mathematicians do like to say things like, oh, well, actually, let me talk about my particular field, which a whole 6 other people in the world understand. But I'll write it on Wikipedia anyway. Mhm. That's what happens. The further you go in math, the fewer people you can talk to about your work. Even now, I spend a lot of time teaching calculus, but I mean, what percentage of the population actually is familiar with calculus? It's really not that extensive. Think about the percentage of people that take calculus in high school. If we want to simplify the problem, let's say you take calculus in high school. Most of the students that take calculus in high school go on to at least go to college. How many people above the age of, say, 25 have a bachelor's degree? What percentage of those people taking a bachelor's degree, take a major that requires calculus? And so they've been even exposed to at least Calc 1 and Calc 2, senior grade calculus. Give you a rough idea of where you sit in the percentile of mathematical knowledge. It's a lot farther up than you would think. Any questions? Comment? Slide them on. You should look up the percentage of people above the age of, say, 25 that have a bachelor's degree. And then try to square that with what you might have been told in high school. You have to have a bachelor's degree. And you think, well, what about the 70% of people that don't? Then think about what percentage of the people that get bachelor's degrees needed to take calculus. And then think, man, I am really far up on this scale. All right. So that was a little tangent I brought up yesterday. It is connected to this tangent line business. It's just go to a higher degree polynomial approximation. And make sure you focus your approximation on a point, x minus x naught, just not x. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.